Assalamualaikum warahmatullahi wabarakatuh, and good morning uh, to everybody. Uh, Today we are uh, going to see chapter 7. The title of the chapter 7 is about combustion. First of all, I would like to thanks to Dr. Azmi Hussein uh, for his effort complete all these slide, okay, for me to show to you about this chapter. In this chapter, uh, we specifically deal, okay, with a system whose chemical compositions changes during a process, that is a system that involves chem chemical reaction. When dealing with a reacting system, we need to consider the chemical internal energy, which is the energy associated with the destructions and formations of chemical uh, bonds between the atoms. The energy balance relations developed for non-reacting systems are equally applicable to reacting system, but the energy terms in the latter case should include the chemical energy of the system. So the in this chapter, we will focus on the particular type of the chemicals reactions known as combustions, because it is important in engineering. So let's look on the objective of this chapter. Actually, this chapter I will be divided into three or four parts. Okay, this is part number one. So when you finish studying this chapter, uh, you should be able, okay, to uh, give an overview of fuel and combustions. That is number one. Number two, you should be able to apply the conservations of mass to reacting system to determine balance reaction equations. And number three, you should able to define the parameters used in combustion analysis, such as air fuel ratio, okay, and this only covered in this chapter 7 part 1. Combustions. Combustion is a chemical reaction during which a fuel is oxidized and a large quantity of energy is released. That is the definition of combustion. As you see in the slide, okay, this is some of the reactant, okay, fuel plus oxygen and also plus heat. Then it will goes to the reactions, example in the chamber, and then the exit product will come as the exhaust and the heat. The oxidizer most often used in the combustion processes is air, for obvious reason, because it is free and readily available. So let's look the next slide. Okay, so as you see in this slide, uh, when we use the pure oxygen, that's mean O2, okay, not air but pure oxygen, as a oxidizer, only is some in the some specialized applications, okay, so such as cutting and also welding. Okay, this is when we use oxidizer as a pure oxygen, but in normally we use air as the oxidizer. So when you look on the mole or a volume basis, okay, we can assume that the dry air is composed of 20.9% of oxygen, 78.1% of nitrogen, 0.9% argon, and other small amount of calcium dioxide, helium, uh, nitrogen, and hydrogen. So for the analysis of the combustion processes, dry air actually approximately as we assume as 21% of oxygens and 79% of nitrogens. This is by mole number. Each mole of oxygen entering the combustion chamber is accompanied by 0.9, 0.79 over 0.21, and it will equal to 3.76 mole of nitrogen. So that's mean we can we can state that 1 kilomole oxygens plus 3.76 kilomole nitrogen is equals to 4.76 kilomole air. During combustions, nitrogen behave as a inert gas and does not react with another elements other than forming a small amount of nitrogen oxides. However, in the presence of nitrogen, greatly affect the outcomes of the combustion process, since nitrogen usually enters a combustion chamber in large quantities at low temperature and exit at a considerable higher temperature, absorbing the large proportions of the chemical energy released during combustions. So therefore, in this chapter, nitrogen is assumed to remain perfectly inert. Okay, but you have to keep in mind that at high temperature, such as those encountered in the internal combustion engines, a small fraction of nitrogens react with oxygens, forming hazard uh, gases such as nitric oxide. Also, air that enter the combustion chamber normally contain a water, some water vapor, or another name is moisture, which is deserve considerations. For the most combustion processes, the moisture in the air and the water that form during combustions can also be treated as an inert gas. Okay, that is some knowledge that you have to know, like nitrogen. So at very high temperature, however, some water vapor dissociated into H2 and O2, as well as into H and O or OH. So when the combustion gases are cooled below the dew point temperature of the water vapor, some moisture condenses. It is important to be able to predict the dew point temperature since the water droplets often combine with the sulfur dioxides that may be present in the combustion gases, forming sulfuric acid, which is highly corrosive. That is one. That is some of the elements that you have to take notes. But in this chapter, we are consider only on the combustions. Okay, combustion, and also the understanding about the calculations based on the chemicals of the combustion processes. Okay, let's look at these pictures. Okay, figures. This is as well as the combustion chamber, where in the combustion chamber, fuel and air is dropped to the combustion chamber, and the products come out from the combustion chamber. So as I mentioned, um, the fuel and air is we know as the reactants, okay, and come out from the combustion chamber known as the product. So if we assume, if we do some exercise here, carbons plus oxygens, it will become carbon dioxide, okay, CO2. And from here, the oxidizer is oxygen. If we use oxidizer air, so the equations will become carbon plus oxygen plus 3.76 nitrogen, because in air it have a nitrogen. Remember previous slide, I said that 1 kilomole of oxygen in air is equivalent to 3.76 of nitrogen. So the equation will become CO2 plus 3.76 N2. Okay, this is the equations for the these chemical reactions. Okay, let's look on name of fuel. Any material that can be burned to release thermal energy is called fuel. Most familiar fuels consist primarily of hydrogens and carbon. So they are called hydrocarbon fuels and are denoted by the general formula CnHm. Okay, hydrocarbon fuel exist in all phases. Some examples being coal, gasoline, and natural gas. The main constituents of coal is carbon. Coal also contain varying amount of oxygen, hydrogens, nitrogen, sulfur, moisture, and ash. It is difficult to give an exact mass analysis for coal since its composition varies considerably from one geographical areas to the next, and even within the some geographical locations. Most liquid hydrocarbon fuels are a mix of numerous hydrocarbons and are obtained from crude oil by distillations. Okay, this is some of the comparison. Okay, uh, between alternative fuels to the traditional petroleum-based fuel used in transportations. Okay, as you see here, gasoline have quite bit energy content. Okay, uh, kilojoule per liter. Heavy diesel. Okay, 35 uh, 800 kilojoule per liter compared to another type of fuels. Okay, ethanol, methane, CNG, and also LNG. Okay, at the left side, this is how gasoline, kerosene, diesel fuel, fuel oil being processed. Okay, so this is a liquid hydrogen fuels obtained from crude oil by distillations. The most volatile hydrocarbons vaporize first, forming that we know as a gasoline. The less volatile fuels obtained during distillations are kerosene, diesel fuel, and fuel oil. The compositions of a particular fuel depends on the source, okay, of the crude oil as well as on the refinery. So the fuel must be brought above its initial temperature to start the combustion. We should also mention that bringing a fuel into intimate contact with oxygen is not sufficient to start the combustion process. So if if it combusts, that means the whole world would be on the fire now. Okay, that's why the fuel must be brought above its initial temperature to start the combustions. The minimum initial temperature uh, in atmospheric air are approximately as listed. Okay, as you see here, for gasoline, the minimum initial temperature must be 260 degrees Celsius. For the carbon, must be 400 degrees Celsius. Hydrogen, 580 degrees Celsius. 610 degrees Celsius for carbon monoxides, and also 630 degrees Celsius for methane. Um, uh, Proportions of the fuel and air must be in the proper range for combustions to begin. That you must also remember. For example, natural gas does not burn in air in concentrations less than 5% or greater than 50%. Let's look on the steady flow combustion process. So in these figures, reactants, when the substance were put into the combustion chamber before come to the combustion chamber, it's called as a reactants. After it's combust or the chemical reactions occur, it will come as a products. Okay. Okay. This is a steady flow combustion process. Um, what I mentioned, the components that enter the reactant chamber is called reactant, and the component that exit are called product. For example, the combustion of 1 kilomole of carbons with 1 kilomole of pure oxygen forming carbon dioxide. We have seen earlier these equations. Here C and oxygens are the reactants since they exit before combustion, and carbon dioxide CO2 is the product since it exits after combustion. Conservation of mass principles, or another name is mass balance. As you all recall from your chemical courses, chemical equations are balanced on the basis of the conservation of mass principle or the mass balance. Which can be stated as following. The total mass of each element is conserved during a chemical reaction. That is, the total mass of each element on the right side hand of the reaction equations, the product, must be equal to the total mass of the element on the left hand side, that is the reactants, even though the element exists in different chemical compounds in the reactants and product. Also, the total number of atoms of each element is conserved during a chemical reaction since the total number of atoms is equal to the total mass of element divided by its atom mass. So, however, you have to notice that the total mole number of the reactant, example 2 kilomole, is not equals to the total mole number of the product, 1 kilomole. So, therefore, the total number of mole is not conserved during the chemical reactions. Okay, this is different from the mass principle or the mass balance. Okay, when you talk about mass, it is conserved during the chemical reactions. But when you deals with the moles number, it's not conserved during the chemical reactions. Okay, please remember that. Now let's see the compositions of a gas mixture, mass and mole fractions. To determine the properties of a mixture, we need to know the compositions of the mixture as well as the properties of the individual components. So there are two ways to describe this composition of the mixture. Number one is by mole fractions, as seen in this slide. Okay, Yi is described as number of moles for individual components divided by number of moles by mixture. That is when we want to describe it as a mole fractions. When you want to describe it as a mass fractions, MFI, so you must use mass of the individual components divided by mass of the mixture. Okay, this is the way to describe the compositions of the mixture. Now we look on the combustion analysis. Um, Air fuel ratio, or in terms of AF, air fuel ratio, represents the amount of air used per unit mass of fuel during a combustion process. So this air fuel ratio is usually expressed on the mass basis and is defined as a ratio of mass of air to the mass of fuel for the combustion process. So this is the formula that been used by air fuel ratio. That means mass of air divided by mass of fuel. So the relation between these mass and number of moles are where m mass is equals to number of mole, that's mean capital N, divided by capital M, molar mass. So if you want to find air fuel ratio, you have to find the mass using the number of moles and also divided by molar mass. But if the name is full fuel air ratio, that means the term FA, this is the reciprocal of the air fuel ratio or opposite of the air fuel ratio. That means mass of fuel over mass of air. So on the examples, okay, of this air fuel ratio and also how to calculate or combustions process in the equation in the questions. Okay, in this example, it shows that 1 kilomole of octane, that's mean C8 H18, okay, not 1 H, 18, is burned with air that contains 20 kilomoles of O2, that means oxygen, as shown in the figure below. Okay, this is the combustion chamber. Assuming the product contain only carbon dioxide, water H2O, oxygen O2, and also nitrogen N2. So this is all the product. The product has X, Y, Z, and W number of mole. The number of reactant is octane, okay, 1 kilomole, and also it use air as a oxidizer. So to solve these examples, first the amount of fuel and also the amount of oxygen in the air are given. So the amount of product and the air fuel are to be determined. Okay. So the assumption that we have to do is the combustion product contain CO2, H2O, O2, and N2 only. So from here you can get the molar mass of air is equals to 28.97 kilogram per kilomole, approximately to 29 kilogram per kilomole. This value you can get it from the table A1 in properties table. Okay, so the analysis you want to start the analysis. Firstly, the chemical equations for this combustion process can be written as below. Okay, so this is the chemical equations. Octane C8H18 plus 20 kilomoles of oxygen, and now it use air for the oxidizer. So air have 1 oxygen plus 3.76 nitrogen in bracket, and the product which is HCO2 plus YH2O plus ZO2 plus WN2. So unknowns are determined by applying the mass balance to each of the elements. Okay, this is the equations, chemical equations. You must make it balance in these equations. So how must you do? So firstly, we see here is C carbon at the left, right, C carbon. C, you also see number 8 here, mole. So 8 here is equals to, okay, try to find at the right side C. Okay, you only see one C at the right equations, one C. So 8 is equals to X, because C and C must be same. Okay, so that's mean to make it balance, it must be same. So 8 is equals to X. So that means X is equal to 8 for carbon. So now for hydrogen. Hydrogen have 18 moles. So 18 moles at the left side. To balance it at the right side, you have to find hydrogen in this equation. Only one hydrogen here, but hydrogen here have 2 moles times Y. That means 2Y. 18 is equals to 2Y. Then solve these equations. Y is equal to 9 for hydrogen. And then go after that, you will see oxygen, O, oxygens. But in here, oxygens have 20 oxygen. So 20 times 2, because oxygen O2, 2 is the mole for oxygen, 20 kilomole must times 2 moles is equals to, at the right side equations, oxygen have 1, 2, and 3. So what happened at CO2, oxygen is 2x, okay, is equals to 2x. As this oxygen is only 1 y, so plus y, this one is 2z, plus 2z. So solve these equations, substitute all the value x and y into these equations, and then you will get z is equals to 7.5. And the last one is nitrogens, N2. Okay, nitrogen at the right and left side is the same, N2. So here N2 3.6 3.76 times 20, 20 times 3.76 is equals to W. Okay, only nitrogen have one only here, so it's equal to W. So W is equals to 75.2. That is the moles for all these substances, okay, or all the gases here. So we substitute all this value into the equations, and it will give the equations, the balance equations like shown. Okay, these are all the values for the moles that have that will be balance the chemical equation. Now to find the air fuel ratio. Note that the coefficients 20 in the balance equations above represent the number of mole of oxygens, not the number of mole of air. So the latter is obtained by adding 20 times 3.76 is equal to 75.2 moles of nitrogens to the 20 moles of oxygen. That means we're giving the total of 95.2 moles of air. Okay, so to find the air fuel ratio, you use the formula air fuel ratio is equals to m mass air over m fuel. So m is capital N, number of mole, times mass of molar mass m for air, same as fuel. In here, fuel is C8H18, C8H18. Okay, so you substituting the values for number of mole for air, 20 times 4.76 kilomole. Okay, why I take it 4.76? This is because it is air, not oxygen. Air is 1 plus 3.76 mole. So it become for air 4.76 kilomole. So time 20 time molar mass of air 29 divided by number of mole for carbon, that's mean 8 kilomole, time molar mass of carbon 12, plus hydrogens is 1. Okay, hydrogen is 1. Sorry, hydrogen is 18 kilomoles, number of mole have in these hydrogens. The molar mass for hydrogen is 1. Okay, if you want to find these all numbers of molar mass of the gases, open properties tables in table A1. Okay, so you can find it hydrogens and carbon molar mass. So calculate it will give the air fuel ratio 24.2 kilogram air per kilogram fuel. Okay, so that 24.2 kilogram of air is used to burn each kilogram of fuel during the combustion process. Okay, that is a simple calculations, and also the simple examples I can show to you regarding with the equations, chemical equations for the combustion process. Okay, I think that's it for this time, chapter 1, part 1. So until we meet again in next class. Okay, but please remember, please read yourself, not just follow these lectures, but also you have to read uh, using reference books that have in the libraries or anywhere that you can find. Okay, read books to get more information about the combustions process. Okay, that's it. See you later. Okay, terima kasih. Assalamualaikum warahmatullahi wabarakatuh.